It is my pleasure to be here today as a plenary speaker. I was born in Banja Luka, but then unfortunately had to leave as a teenager. For the last 30 years, I've lived in the US, and today I will be talking about innovations in architecture, research, design, and technology. So our agenda for today, first we'll talk about innovations in architecture. What do I mean by this? Some background information. Then I will show a few examples from practice, integration of R&D with design, focusing on global projects. And then we'll talk about research examples, specifically advanced materials, digital fabrication, performance-based design, smart buildings, and regenerative buildings. At the end, we'll talk about some of the challenges facing the architectural profession globally, and then some of the opportunities. At the end, we'll have some time for Q&A, and I would like this to be as interactive as possible. So please, if you have some thoughts, ideas, comments, questions, write them down, and we will have a discussion at the end. Thank you so much for the introduction about me. These are the books that I've written. Research Methods for the Architectural Profession was published in 2021. Integrating Innovation in Architecture was published in 2017. Future of Architectural Research was published in 2015 by Perkins & Will, global architectural firm, where I was directing the R&D department. And Sustainable Facades was published in 2013. Sustainable Facades was translated to Chinese language. Obviously, I don't speak Chinese language, but it was interesting to see that book reach global markets as well. These are examples of some of the projects from professional practice. I'll talk about one of these projects, Russian University Medical Center, Chicago. But most of my professional experience includes higher education buildings, museums, civic buildings, everything but a single-family residential building. Most of the talk and presentation today will focus on material from this book, Integrating Innovation in Architecture. This book introduces methods for integrating new materials, technologies, R&D in architectural practice. What's really interesting about this work is I interviewed around 70 global firms, some well-known, some unknown, large-scale firms, medium-scale firms, because I was trying to answer this question, what is innovation in architecture and how do we innovate? Obviously, there's not a model that fits all of the different practices, but that was the underlying goal for this particular work. And then, building upon that work, Research Methods for the Architectural Profession, my most recent book that was published in 2021, really specifies methodologies for executing research studies, how do we do and connect research and scientific research to architecture, and provides guidelines for executing research studies. I'm not really sure what textbooks you use here, especially for PhD students, maybe master's students. In the US, prior to this work, the book that was used was published in 1992. Back when I was a PhD student, back in the day, that was still used. It is outdated, not really reflective of the contemporary challenges in the architectural profession, so that was the reason why I decided to write this work. So what is the model for integrating innovation in architecture? I mentioned that I interviewed 70 different firms trying to address this question. There's not a model that fits all of the different practices, but research and development needs to connect to the design. It also needs to connect to investments and culture of the firm. So new materials, building technologies, construction technologies are very important. BIM, digital fabrication, computation. And then innovative firms need to invest in R&D and develop culture that really supports experimentation and integration of research in practice, which is challenging. We can have a separate symposium on challenges that architectural firms face when they try to integrate research and development and innovation. Throughout this research, I realized that there are some similarities among different firms that are innovative. Inquiry, analysis, integration of research with the design process, high technical aptitude, then integration of design, different design methodologies, technologies, and then communication and dissemination. Something that we are not doing really well globally, even research coming from practice, relies to publishing research results. It was mentioned in the beginning that I was one of the founders of the first research journal, peer-reviewed research journal coming from architectural practice, and that was the reason. Okay, we do research, but how do we collect that information and how do we disseminate and communicate to the broader design community, but also to broader public? The last sort of introductory slide relates to integration of research into design practice. What are the different models? There's the internal model, external, and hybrid. Internal model basically means that the R&D department is integrated within the architectural firm. That's an example of the building technology lab that I led for Perkins & Will for years. That means that researchers are part of the firm, they're integrated into the design process, they work on projects and so on. The challenge with that is, how do you pay them? Where does the funding come from? So only large-scale firms like Perkins & Will, SLM, HKS, HOK, Gensler can really utilize that particular funding model. The external model means that a design firm might collaborate with an R&D entity, whether a university, national lab, and smaller scale architectural firms are utilizing this model. And then the hybrid model basically means that the architectural company might open up a separate nonprofit department focusing on R&D activities. There are not that many, but a few large-scale firms in the US have realized the potential as a nonprofit entity basically to qualify for federal funding to work on research projects. So Perkins & Will has a sister company called Area Research, that is basically engaging in different types of research studies. SLM, another large-scale, famous US architectural company, also has sort of a nonprofit R&D sister company. So now I would like to show some of the examples from practice where research directly integrated into design process. The first example is Shanghai Natural History Museum in China. This was a design competition that Perkins & Will won in 2005, 2006. And the idea was really to reflect on the site and location of this project. You see the site plan on the right. It's located right in downtown part of Shanghai, which is kind of an interesting concept. Downtown part of Shanghai is as large as, I don't know, 4 times the size of Belgrade. But it's located in a botanical garden. So how do you take that sacred space and how do you design a museum that really fits in within a larger density? So the idea was to really sort of extend the landscape. You can see the large green roof that was designed as kind of a walking surface for pedestrians, museum attendees to be able to explore the 5th building envelope, really the roofing. Many different sort of innovative design approaches were utilized, vegetated facades on different building enclosures. But the central point that I really want to talk about here is what we call cell wall. You can see this large curved wall that encompasses a garden and provides like a central atrium and a courtyard at the bottom part of the building. You can see here different plans and section. I don't think that the laser pointer works, but here are different floor plans and sections. So the cell wall and this curved wall was really designed to provide daylight and connection, visual connection to the central part of the museum. And because it's a natural history museum, we wanted to use biological forms, biomimicry, to enclose that curtain wall. And it took probably 14 months of planning, research and development and design to really execute this. This is especially for students in the audience. I don't know how many students are here, but with the new computational tools, we can design any geometry, right? We can model any geometry that we want, really complicated and so on. But how do you make it a reality? How do you construct it is a big challenge. So you can see here aerial snapshot of the garden, the cell wall, the curved wall, encompassing the courtyard, and you can see the intricate design. So basically the design procedure was to utilize a pattern that repeats and to make it easier to construct, because this cell wall is 5 stories high. So how do you solve structural problems, wind loads? That was quite a challenge. You can see partial section in large elevation and a plan of that curtain wall. The pattern looks as if it's irregular by logic, but there is actually logic to that, because we spent so much time rationalizing this particular complex geometry and trying to figure out how do we solve it, how do we develop the framing, how do we develop the rain screen system. So there are essentially 3 layers. And then another challenge is that the cell wall curves in 2D in plan, but also curves in 3 dimensions as well. So think about joints and movement and thermal behavior and so on. So on the exterior, there's an aluminum screen, then aluminum skeleton system basically supporting the screen, and then regular curtain wall on the inside. And you can see sort of the interior view through the cell wall. Another example from practice is Rush University Medical Center, located in Chicago. So the design of this particular hospital started in 2006 and it was finished in 2013. Those of you who are from Belgrade might recognize the shape and form, but I'm not really sure if the head designer was aware of similarities. The bed tower, it's a huge hospital, 100,000 square meters in area. And the butterfly shape was developed to basically minimize the amount of walking that medical staff has to do. Typically, hospitals are designed as rectangles, U-shape, and so on, which means that medical staff, doctors, nurses, and so on, sometimes they walk 25 miles, which is like 35 kilometers per day, serving the patients. So the butterfly shape was developed basically 4 different parts of the building. All of the central services, nurses station are in the center, so each team serves only one arm of the butterfly. During the design process, we did studies. This used to be a parking lot because there's an existing hospital right next door that was built in 1960s, where we used duct tape to basically outline the footprint of the building, the butterfly shape and then different shapes. Then we called hospital staff, doctors, nurses, and so on, and then we used just a stopwatch to measure the amount of walking. Observational and experimental study. You can see here the building during the construction. But what I really want to talk about is a special place, entry pavilion. You can see the East Tower, this large butterfly-shaped hospital, existing building on the west side that was built in 1960s. The client realized during the design process that there was this empty space in between the buildings and what to do with them. Because Rush University Medical Center is associated with the University of Chicago, so very large. They have at least 30 different buildings on this particular campus. So they wanted to create welcoming space, sort of celebratory space, and the main entry point into the medical campus. So you can see here the scale and size. The East Tower is very large and complicated, and today, unfortunately, I don't have the time to talk about all of the intricacies that went into the design of that space. But the entry pavilion, as you can see, it's a much smaller space, but very special. Something that we wanted to do, we wanted to follow Living Building Challenge sustainability rating system. How many of you are familiar with Living Building Challenge? Okay, so I'll explain briefly. How many of you are familiar with LEED? 1, okay. So LEED is a globally known sustainability rating system for environmentally friendly design. It started in the US and Canada, but now it's used internationally as well. Living Building Challenge is another sustainability rating system, which is much more stringent than LEED. It requires that buildings are designed as net zero energy buildings, net zero water buildings. And then it also has sort of a red list of materials that have a negative impact on human health, and they're prohibited to be used in buildings. So Living Building Challenge has been around for the last 25, 30 years. Buildings that have been certified up to date tend to be very small scale, single family residential buildings. A building of this scale and size, even the Energy Pavilion, it was never designed because it's challenging. Net zero energy is challenging but doable. Net zero water, very challenging, doable. But the problem is the red materials list. Like galvanized steel, for example, is on that list. So if you cannot use it, what else are you going to use it? So anyways, we use that as a research process to investigate how can we meet Living Building Challenge on this particular project. And it's very hard to see, but there are different categories related to site, building systems and energy, water usage, materials. The last category is beauty. So buildings are also characterized and scored based on the architectural quality and the design. So during the design process, we did a couple of different research studies to really investigate how do we meet Living Building Challenge for this particular building, understanding shadow ranges and shading, daylight analysis for the lobby and terrarium, solar exposure for different facades, double skin facade design for the bridge connecting the existing building to the east tower, and then we did a performance study of including photovoltaic systems for generating electricity. So quickly just showing shadow ranges, because as you can see in this sectional perspective, on top of the entry pavilion, we have an accessible garden, and the garden was really meant to bring in nature and provide nature for medical staff, visitors, patients, and so on. And you can see this terrarium, and this is basically completely open to the nature, but the idea was, okay, let's bring the nature to the lobby space and create like a livable organism inside the building. So the question for shadow analysis was, Chicago is very cold in the winter. The question was, are we going to have any sunlight for any types of plants to grow on the green roof? And then especially for the terrarium, because you had these two large masses blocking the sun and daylight, and the question was, what would be the effect of thermal comfort? Would there be enough daylight? So you can see here in the terrarium, okay, this is completely open to the elements, open to above. We have a tree, we have grass, but the question was, are we going to have enough sunlight reaching the ground surface for any plant, any types of plants to grow? So we did daylight simulations. So on the left side, there's a plan, and then on the right side, there's a sectional view through the terrarium, basically showing daylight levels. It was really interesting that the daylight simulations showed very high amounts of daylight, because there were 3 skylights that were planned, and then we decided to use basically translucent glass to minimize the potential for glare and daylight, and the design team could not believe that the daylight levels would be so high. So after the building was constructed, we went back and with the light meters, we measured the lights. And discrepancy between simulations and sort of real measured data was like 5%. This is the terrarium during construction. Again, for students, especially with the advanced digital tools, we can generate any shape and form, but when you try to make it a reality and construct it, it becomes messy. So initially the curvature of the terrarium was different. We had to change it during the design process, rationalize it to be able to frame it, to design the curtain wall. That took a lot of time and effort. And here's the constructed and finalized terrarium. There's also a system within the terrarium that melts snow automatically. Again, it snows a lot in Chicago, right? So how do you shovel snow from that space? So there's a system also installed that can maintain the snow in that area. Double skin wall, glazed double skin facade was proposed for the bridge connecting the two to the two buildings. In the US, building codes prohibit the use of natural ventilation in hospitals. That's not the case here, right? So operable windows cannot be used. Any part of the hospital that has medical procedures needs to have essentially fixed windows and closed windows, and the reason is infection control. So buildings in the US medical centers rely just on mechanical ventilation, mechanical heating and cooling. So this is a lobby space, so we actually wanted to use this as a strategy to naturally ventilate and to improve the energy consumption and to meet the living building challenge. So we looked into different options for a double skin facade, varying the depth of the air cavity within the double skin, the type of glass, operation mechanism. Here are all the results showing impacts on energy consumption on an annual level, heating loads, cooling loads, and so on. We found basically the design option that would save 70% of energy compared to a single skin. Well, the client also wanted to understand the cost, benefit, and impacts. After we conducted the energy modeling, we also conducted cost analysis and found out that it would take 95 years for the double skin to pay itself. Guess what happened? Did they include it? No. So I think that this is one of the challenges that you're facing here, anywhere in the world, right? The client is always interested in, okay, advanced technology, advanced system, advanced material. Sounds really great. What exactly is it going to cost me? What are the benefits? And then based on my experiences, because I have done studies like this on at least 120 different projects located around the world, if the cost payback is less than 10 years, it's easily integrated. If it's between 10 and 30 years, it depends on the client. More than 30 years, no way. Even the most innovative, beautiful design technologies are very challenging to be integrated. So double skin was not included in the project. Photovoltaic study, we were investigating, basically covering half of the roof of the existing building, half of the roof of the east tower, two large PV arrays facing south. We did solar radiation analysis, cost analysis. Well, we found out that, okay, investment would be $2 million for the PV array, but then the PV array would be able to cover 1% of the energy demand for the hospital. Was the PV system integrated or not? What do you think? It wasn't. It wasn't. The client was, oh, that's going to cost too much money. The payback is not really realistic. So again, realities of innovating in practice. And these are the final images of the hospital, final images of the terrarium skylights, the garden on top of the terrarium. It's still a beautiful project, but a lot of innovative things that we were considering were not fully integrated because of the cost and economic impacts. Now I would like to switch to research examples. Let me just check the time. Okay. I want to keep talking. Okay, so let's talk about research and some of the research projects. So the first project that I want to talk about is, this was an adaptive reuse project. It was a cold storage facility located in Chicago, just 2 miles, roughly 4 kilometers west of downtown Chicago. Historically, that was a meat packing and industrial area in 1800s and 1900s that in late 1990s started to redevelop. Basically, the zoning was changed from industrial to mixed-use residential and commercial, and a lot of new buildings as well as renovations of existing industrial buildings into residential areas or commercial took place. Right now, in 2024, so this is called West Loop. West Loop is the hippest area of Chicago, like similar to Soho in New York. So anyway, so this building was built in late 1800s. It was a cold storage warehouse. So no windows, you can see windows just on the perimeter for stairs. The rest of the building, no windows, because it acted as a huge cold refrigerator, basically for storing food. The client bought this building and wanted to convert into commercial office space. So we use this as a research project to investigate parametric design methods, integration with performance-based design and simulations, and digital fabrication. And we focus just on the building skin and facades. And also we wanted to test different types of advanced materials and how they can be used. We also, at that time, I was actually at Perkins and we collaborated with the university. So remember when I talked about different research, different methods and different models for integrating research, that was basically sort of an external design firm integrating with university. So this was the process. We gathered all the initial construction documentation. The original construction document that was used for permitting in 1800s had 16 sheets, just 16 drawings. And then we developed a Revit model. Then we used different types of advanced modeling software programs, Rhino, Revit, 3D Max, Maya. And we wanted to basically test parametric design processes. How do we integrate them with simulations and modeling? How do we use that data to directly feed into parametric modeling tools to create building facade elements and control geometries of facade elements, shading methods, and so on. And then at the end, we also used digital fabrication method to test and develop these prototypes. So that was the process. And here's an example of one particular solution. So you can see simulation results for solar radiation. Ecotech software tool was used to basically generate solar radiation. That data was then directly fed into Rhino through Grasshopper to develop facade elements. And then where you need more shading, these openings are larger. Where you need less shading, they're basically smaller. Sort of the depth of facade materials and assemblies was automatically generated and controlled by parametric tools. And then, as you can see here, so it's regular glass, but then the shading system, this kind of triangular form, utilized GFRC, glass fiber reinforced concrete method. And here's the testing procedure for digital fabrication. So we use CNC milling, we use laser cutting, different techniques. Here's the digital fabrication method that we used basically to generate full-scale mock-ups. I also want to briefly talk about augmented reality and virtual reality in architectural design. You're probably familiar with these tools. They have been around for some time, but they have huge potential to be used in architectural design as well as education. So we have different techniques to integrate virtual reality, especially Samsung Gear, VR equipment, Oculus Rift, and so on. Some firms are already integrating this, and I think in the US, architectural industry is actually better moving forward in the use of these advanced technologies than the architectural education. So what we wanted to really understand is augmented reality and then virtual reality, and how does the designer use these tools to visualize, to understand the spaces versus the client. And then we also did a study where we showed these models to students to see how they like this and is this sort of a promising technology for architectural design. So we developed different models for conceptual design, schematic design, design development, and what was varied is the amount of information embedded in these digital models. So the design development model had a lot more information. Detailed building envelope, integration building systems, materials, and then we did walkthroughs to really understand, with a headset, completely in immersive environment, how do you visualize the space? How do you move the space through the space? Is it beneficial to the designer? Is it beneficial to the client? So here are the examples of experimentation. You can see the AR model was just basically displayed on a tablet. VR model was fully immersed with the virtual reality headset, and then we did evaluations. Each evaluation lasted about 30 minutes, where either the designer or the client would walk through virtually the building through different spaces and understand. And here are the results. I I will briefly summarize. Augmented reality is beneficial for early conceptual design, massing studies, understanding buildings' scale, size, integration with the site. Virtual reality is really beneficial in later design stages, and it's especially beneficial for communication with the client. There's no other visualizing sort of technique that we currently have that is as capable as virtual reality. Because even a 3D BIM model, if we see it, we just look at it. I mean, it's still augmented reality, right? But when you put the headset in, when you walk through your building, it is just an amazing experience. Understanding scale, materials, quality of light, movement, and I truly believe that in architectural education, we should use these methodologies more often and teach the next generation of architects to be innovative and use innovative techniques. And here, this was kind of an interesting, we also did evaluation with students. We asked them beforehand, are they familiar with AR, VR tools? What do they think about it? Most of them were not, like they heard about it, they never used it, and then we did an evaluation with them to basically walk them through the model, to walk them through this digital space, and then all of the students were like, whoa, this is amazing, this is like understanding again scale and so on. So professors in the audience, spending some time and learning about this and integrating in architectural design studios and so on, because this is really the future. The next project, briefly, smart buildings, smart facade systems. We developed a system for smart facades that integrate thermoelectric materials. Thermoelectric materials utilize temperature gradient to generate heating, cooling, or electricity. So we started this particular project with an experimental study. Okay, nobody ever thought about including, because thermoelectric modules exist, they have been around for the last 20 years. But if you think about buildings, you always have temperature difference between the inside and outside of the building. And what if we use that temperature difference to power thermoelectric materials in the facade to generate heating or cooling? So we started with the prototype experimental studies in a thermal chamber, measuring heating, cooling output. Results were actually a lot better than we thought they would be. Then we did CFD simulations to understand heating and cooling potential within the interior space. So think about this as a sort of a smart facade system that just uses temperature difference to power and generate heating and cooling. Then we developed real facade systems to integrate this into green screen facade systems, into shading mechanisms, into curtain wall and a spandrel area in between. We have a patent pending for this particular technology. And then real prototypes. You can see smaller scale digital prototypes. And then full scale working prototypes that were used for testing and measuring. Since then, we also did simulation study to understand benefits on heating and cooling in different climate types in the US, from Miami all the way to Alaska. You can see some of the results here. It's a really advanced and cool technology that I hope will someday see wider application and integration in buildings. And then quickly, regenerative buildings. This is kind of one part of my research study, is focusing on adaptive reuse and existing buildings and ways to improve their performance. Many buildings in the US have been abandoned, like we call these post-industrial buildings, right? This was located in Massachusetts, previous university where I was before the University of Utah. This was a paper mill company. Again, the building was built in 1800s, reconstructed in 1920s, 1960s, and so on. Right now, only 10% of the building is used. So we wanted to investigate how do we renovate this, how do we change the building function, and how do we meet net zero energy goals. This is our design solution. We did an analysis of structural systems because the building was basically added to different time periods. So we kept what we could keep. We demolished what was not structurally viable, and then you can see fifth floor added as a commercial. We also changed the function of the building. We introduced residential, commercial, retail spaces to this building as well. You see here the other side of the building. study and energy modeling, we understand how to meet and manage our energy goals. Even with the largest solar array we could fit, we only were able to produce like 45% of the energy needs for the building. So we needed to add wind power, biomass for the heating, and then hydro energy. The building is located near a river and a canal, and then the city where it's located in 1800s used to be like a major industrial area, and in 1800s, 95% of the energy was basically hydro energy. Most of those turbines do not work anymore. So we really just find one turbine. And then the last case study focusing on regenerative design. This is the university building, the University of Massachusetts. It's a research laboratory building, and it's actually two parts of the building. The original building was built in 1947. It's in orange on the north, and then whatever is in purple was built in 1974. So we investigated initial spatial organization, structures, central systems. What's really interesting, on the 1974 part of the building, there are no windows in the research laboratory space. And then there's an atrium in the middle, and then the circulation space. As you can see in the side plan, this is like the main pedestrian pathway for everyone walking from the east side of the campus to the west side of the campus. So this is our design solution. Replanning the building, taking out the central component, bringing in a newly designed central atrium, includes a double skin facade, and then on the research part of the building that was built in 1974, introducing windows, introducing solar wall, improving building envelope, and then in terms of other systems, including fuel cells, as we renewable energy system, clean roof, triple glazed, glazing system, EV panels, and this was basically our retrofitted design solution. You can see the diagrams that improve circulation, improve spatial configuration of the building, but also architectural design. Here are the energy modeling results. We did an energy model. We compared the actual energy consumption of the building. And then we also did an energy model of the retrofit solution. So we really investigated the changes to the building envelope, changes to the building systems, how do they affect energy usage. Thermal imaging in Massachusetts is very old, so we did thermal imaging to understand the facade systems. Building built in 1974 does not have an insulation whatsoever. So yeah, it's solid. There facade, no windows, but it was horrible forming. Building built in 1940s, single layer of glass. Students would actually cover plastic film or something because it was in the meantime would be very cold. So now see the facade system existing, what do we change, understanding thermal performance, understanding how do we preserve, how do we add. So we actually use a solar wall system that can heat air and redistribute interior spaces. Thermal analysis of windows and glazed parts of the facade. You can see the original facade and then we added. And then moisture, air and moisture transport, because whenever you're adding insulation from the outside, the question is always condensation problems and so on. So very detailed analysis of that system. Briefly, we are extending this type of research studies and looking into holistic commercial buildings, residential buildings in the U.S., ways to achieve net zero energy, but also cost. So I know PhD student presentation focuses on optimizing design strategies and renewable energy systems, looking at costs and how do we achieve net zero in gradually existing buildings and how do we optimize economic impacts as well. So briefly, challenges. Increasing complexity of projects. This is globally present. Rapidly evolving technologies. It's difficult to innovate. Climate change, economy, cost paybacks, inefficient existing buildings. And then opportunities. We can use advanced technologies and solutions to meet these types of challenges. Regenerative design, focusing on really improving existing buildings as much as possible. Intelligent building systems and smart buildings. Computation